Hey everyone! So previously we have seen that alcohols made the homologous series which had the hydroxy functional group which was the OH. We even saw how the dot and cross diagram of an alcohol compound was made because there were carbon atoms making dots and crosses with the oxygen atom and the hydrogen atom. The oxygen had to be attached to the carbon. And we even saw that they were not hydrocarbons anymore because they also contain an oxygen atom. We saw their general formula, which was CnH2n plus 1 OH if you want to write the OH separately, or it could be CnH2n plus 2 then a single oxygen atom. We even tried the naming and the formula making for methanol, which was CH3OH, and similarly for other alcohols as well. We then tried the formula making for butanol, which was a C4 alcohol, and similarly pentanol and hexanol. In today's video, we're going to try the idea of oxidation of alcohols. So what is oxidation? We know that oxidation means multiple things. It is first the loss of electrons. So the foremost definition is oxidation, loss of electrons. Similarly, oxidation is also the loss of hydrogen atoms. So loss of hydrogen. And the third definition is it is the gain of oxygen atoms, or you can simply say oxygen over here. So when we talk about the alcoholic oxidation, we're going to try a compound first. Let's say I have a molecule which has two carbons over here, and there is an OH functional group, which is the hydroxy functional group. We know that this is ethanol because it has two carbon atoms, C2H5 and then the OH over here. Now if we want to oxidize these alcohols, we have to focus on the carbon which has the OH. We have to be very focused on this particular carbon that has the hydroxy functional group. After oxidation, the hydrogen atoms are lost and oxygen atom is gained. So the number of carbon atoms remain the same, but the carbon under focus loses the hydrogen atom. So hydrogens go away from that particular carbon which has the OH attached on top of it. And then the other carbon remains the same, so no changes on that. OH remains the same, but once both the hydrogens are gone, on that central carbon we attach something new over here, and that something new is an oxygen atom with a double bond with the carbon atom. So when the hydrogen atoms go away, we have space for a new atom, and that is oxygen atom that connects itself to my central carbon. So oxygen atom joins in. This is how alcohols are oxidized and we get something new. This new compound is also an ethane because it has still two carbon atoms over here, but it's not an ethanol anymore. It becomes something new, which is the ethanoic acid. So ethanoic acid, or we are going to see later that it's a carboxylic acid. Similarly, if we have a propanol over here, we again focus on the carbon which has the OH. We remove the hydrogen atoms from that particular carbon, and then we attach an oxygen atom with a double bond. It's a member of a new homologous series, which is the carboxylic acid homologous series. So it's not a part of the alcohol anymore, it's a part of the carboxylic acid homologous series. We have to notice that it still has three carbon atoms, so the name is propanoic acid. Similarly, we can do this process with any other alcohol. For this particular compound, the formula becomes C3H6O2. Let's say if we had a butanol molecule with C4, we again remove the hydrogen atoms from the particular carbon, we attach oxygen atom on that exact carbon, and now it becomes butanoic acid, which has 2 less hydrogens and 1 more oxygen. The formula becomes C4H8O2 because the carbon is still the same, but we are losing 2 hydrogens and we are adding 1 more oxygen atom. So C4H8O2, butanoic acid. The idea remains the same. Now, if we have to talk about the experimental analysis, if we have to talk about the experimental requirements, so we can see the idea of oxidizing agent which is required. So alcoholic oxidation experimentally requires, let's suppose we have a test tube over here, then we have the alcoholic sample, let's say it's any alcohol, ethanol, propanol or butanol. We take a dropper which has acidified potassium dichromate. It's a very strong oxidizing agent. When we add the drops, it changes the color from orange to green. Potassium dichromate was initially orange, but it changes color from orange to green, which indicates that the alcohol has been oxidized. For example, if we had methanol, it becomes methanoic acid, where an oxygen atom joins in. If it was ethanol, it becomes ethanoic acid, and if it was propanol, it becomes propanoic acid. Every time a new oxygen atom joins in. All these oxidations require a hydrogen ion and potassium dichromate. This introduces us to a new homologous series, which is the carboxylic acids. Let's revise that it's a new homologous series of organic compounds. It's not hydrocarbon anymore, obviously, because it has oxygen atoms. So homologous series of organic compounds that have the carboxylic acid functional group. So it has the carboxylic acid functional group, which can be written as C double bonded oxygen and then OH, or you can simply call it COOH. This is the carboxylic acid functional group. So all the carboxylic acids have to have this particular functional group, C with a double bonded oxygen, and on that exact carbon you have another OH. The fourth bond could be anything. And now this is another functional group that we have introduced in our organic chemistry series so far. We're going to talk more about the carboxylic acids and why we call them acids in the upcoming videos. So stay tuned, guys.